Hi, in this video we are going to discuss some problems on simple harmonic motion. A card attached to a spring is displaced from equilibrium and then released. A graph of displacement as a function of time for the card is shown. There is no friction. Points are labeled A to H in the graph. For each question below, choose from the labeled points above or state none for the mass spring system. Look at this diagram. The spring card system is set on a horizontal surface. So the force of gravity acting upon a car is immaterial. This is because the downward force of gravity will be completely balanced by upward reaction from a ground. So the cart will be moving only under the influence of spring force. The cart will be performing simple harmonic motion in a horizontal direction. The question is, at which point or points are the spring potential energy and cart's kinetic energy both at their maximum value? Only two forms of energies are involved in this motion: kinetic energy and the potential energy due to spring. During the motion, kinetic energy and potential energy simply convert into each other to keep the total energy constant according to the principle of energy conservation. So because kinetic energy and potential energy simply convert into each other, they cannot both reach maximum or minimum value during the motion. There is no point in the motion at which the kinetic and potential energy can both be maximum or both be minimum. If one is maximum, other will be minimum. So the answer to this question is no such point in the motion. Now, we can explain it. According to principle of energy conservation, the potential energy and kinetic energy convert into each other to keep the total energy constant. Total energy constant. And hence, the two cannot be both maximum or minimum at any point in the moment. Question B, at which point or points is the kinetic energy equal to zero? Cart is performing simple harmonic motion in a horizontal direction. When cart is at a maximum distance from its equilibrium position, it comes to a momentary halt at a maximum distance from equilibrium position on both the sides of equilibrium position. So when it is at a momentary halt, its kinetic energy will be zero. The kinetic energy will be zero at extreme position at maximum distance from mean position on both the sides. So if you look at a graph, point A represent maximum displacement from mean position. And this happen at the moment of 8 seconds. Point A represent maximum displacement on one side of the equilibrium position. Point E represent maximum displacement of the same magnitude on the opposite side. It is the point A and E at which the kinetic energy will be zero. We can reason it like this. This is the reason why kinetic energy have to be zero at extreme position, maximum distance from the equilibrium position. At maximum distance from the equilibrium position, the card cannot move further because that is the maximum distance it can move from the equilibrium position, and hence its speed is zero there. Therefore, its kinetic energy also zero. I wrote this answer in a wrong place. Is the answer to the question B. Now it's fine. Question C. At which point or points is the total energy at its maximum? Total energy is simply constant throughout the motion. So it cannot have maximum or minimum. We can alternatively we can say that the kinetic total energy is maximum everywhere. Saying that the total energy is maximum everywhere, we are in other words stating the same fact that the total energy. But we prefer to say that the total energy is not maximum anywhere, it is simply constant. So there is no such point where total energy is maximum. We explain the fact that the total energy is not maximum anywhere like this. The reason is that according to the principle of conservation of energy, the total energy is constant throughout the motion. And hence total energy cannot be maximum or minimum anywhere. Well, you might want to include the third form of energy, which is the potential energy due to gravity. But as we see that the car is moving on a horizontal surface, so the level of the car remains the same. And that's why its potential energy due to gravity will not change. Potential energy due to gravity, which we call gravitational potential energy, it changes only when we either lift the object or lower it. Only when the height of the object relative to the ground changes that the gravitational potential energy changes. But here the card is remaining at the same level, so no change in gravitational potential energy, and we can choose this level of the card, the level upon which the card is moving. We can choose the gravitational potential energy to be zero at this level, because to begin with we can choose any arbitrary value for the gravitational potential energy at any particular point to begin with. So at this level, you can choose the gravitational potential energy to be zero, and the only two forms of energy we will have to deal with are the kinetic energy and the potential energy. However, gravitational potential energy will also play a role when the height of the car were changing relative to the ground, and this happens when an object is suspended by a spring and hanging under gravity or oscillating in a vertical direction. That case, gravitational potential energy will also have to be included in our description. Question D. At which point or point is the spring potential energy negative? The spring potential energy could be negative. It depends upon what value for the spring potential energy you choose at a reference point. We choose potential energy to be zero at the main position, and it is minimum at the main position. Potential energy is minimum at the main position or the equilibrium position, and it increases as an object moves away from the main position on both the sides of the equilibrium position. Main position is the same as equilibrium. So if you choose potential energy to be zero at equilibrium position, which we represent as x equal to zero, then potential energy only increases as the object or car move away from the main position. Potential energy increases means the potential energy will have values greater than zero. Potential energy will have values greater than zero means potential energy can only have positive values and the zero value at the main position. The potential energy cannot be negative anywhere. So the answer is none. It doesn't mean that the spring potential energy can never be negative. It just depends upon the choice of potential energy at a particular reference point. We choose potential energy to be zero at mid position. Potential energy is never negative anywhere with this choice of zero. However, you can choose to represent potential energy due to spring to be negative value at main position. For example, say minus 10, negative value. Then potential energy would increase again as an object move away from the main position. Potential energy will be higher than minus 10. So even minus 3 number represent the value higher than minus 10. So you can still continue to have negative values uh, for the potential energy in a simple harmonic. But we choose potential energy to be zero at main position, so we not have negative values for potential energy. Have only the values higher than zero, positive value. We explain our answer with this reasoning. I have written the reason for our answer. It is the same reason that I have already explained. Question E. At which point or points is the kinetic energy positive? Kinetic energy is always positive. It can never be negative because kinetic energy involves square of the velocity. So square is always positive. Kinetic energy also involves mass. Mass is always positive. So kinetic energy is always positive. It cannot be negative. If you make kinetic energy negative, it would mean that while mass is positive, v square must be negative, and v square can never be negative. Kinetic energy is equal to half mv. Kinetic energy is always positive. So the question is, at which point will is the kinetic energy positive? Kinetic energy is positive throughout motion, except when the car is at extreme position, where the kinetic energy is zero. So we can write it is everywhere. It is everywhere positive, except at extreme position. But we have to answer this question with respect to diagram shown. So we must mention the points from the diagram where kinetic energy is zero. Kinetic energy will be zero at A and at point E, and everywhere else it is positive. Extreme positions are A and E. Question D. At which point or points is the kinetic energy at its maximum value and spring potential energy is at its minimum? Kinetic energy is maximum when a car passes through equilibrium position. An equilibrium position is the position which we design it as zero. So all the points at which the curve intersects time axis, those points represent equilibrium position. Kinetic energy will be maximum at the position C and G, and correspondingly the potential energy will be minimum. Points D, C and G. This is the reason why kinetic energy is maximum and potential energy minimum. The point at which kinetic energy is maximum, the potential energy must be minimum, because the sum of kinetic energy and potential energy is the total energy is constant throughout the motion. The total energy is constant means whenever you have maximum kinetic energy, you must have minimum potential. Question G. At which point or points is the kinetic energy minimum and spring potential energy at maximum? Kinetic energy is minimum at extreme position. The positions represented by the point A and point C. Kinetic energy is minimum there, and potential energy must be maximum for the reason that we have stated in the previous question. Answers are A and E, and the reason is similar to the one that we stated while answering the previous. Next question. A mass on an air track attached to a spring complete one oscillation every 2.4 seconds. Now mass is moving on an air track. It means the friction is nearly zero. We can ignore it. And one oscillation is completed every 2.4 seconds. So time period is 2.4 seconds. At t equal to 0, the cart is released from rest at a distance 0.10 meter from its equilibrium position. What is the position of the cart at 0.3 seconds? We first write data. We are given time period 2.4 seconds. Every oscillation is completed in 2.4. Time period is 2.4 seconds. It is given that at time t equal to 0, the position of a mass is 0.10 meter from the equilibrium position. And at this position, at this distance of 0.10 meter from equilibrium position, the object was simply released from race. So it had no speed at that point. It means that it is the maximum distance from equilibrium position, and therefore it represents amplitude. Because there is no friction, the mass will travel, the mass will pass through an equilibrium position and start moving in the opposite direction. And it will come to a halt on the opposite direction exactly at the same distance A, because there is no friction. It will turn back, reverse its direction of motion from an extreme position on the other side, will again start moving toward the equilibrium position, and the oscillation will keep going. The maximum distance from the equilibrium position will always be 0.10 meter on either side of the equilibrium position. We have to find the position of the car at t equal to 30 seconds. To find position at t equal to 0. Formula that we can use to solve this problem. The formula is an equation that describes simple harmonic motion of the mass, and that formula is Ax equal to A sin omega t plus 2. Well, we can also use another formula. That formula is x equal to A cos omega t plus theta dash. This formula can equally well be used to solve this problem. You can remember any one of the two formula, whichever formula you find suitable and easier to solve, you can use that formula. But we use this formula x sin omega t plus. It's just a choice, and there is no special reason why I choose sin over cos. You can equally well go with cos. We first note the quantities that are given. We are given amplitude, which is 0.10 meter. And we are given omega. Omega is not given directly, but rather we are given time period. And we can find omega from time period by using a formula. I will state solution. So omega is basically given. Time at which we have to find the position. We have to find position at a particular time. The time given is 0.3. Theta is not given. Unless we find out theta, we cannot find out position, because there will be two unknowns. X is already unknown, theta will also be unknown. So all the quantities on the right hand side must be known. We do not know what is theta, so first we have to calculate theta. Theta is not given, but theta can be determined from the initial condition. Initial condition is at time t equal to 0, the position is 0.10 meter. So we can substitute for time t equal to 0 in the equation, and for x we can substitute 0.10 meter, and then we can substitute other quantity and obtain the value of theta. We rewrite this formula: x equal to A sin omega t plus theta. We first find theta. To find theta, substitute x equal to 0.10 meter when t is equal to 0, and then we get x equal to, we have to substitute other quantities also, but before we go for substitution, we rewrite this formula replacing omega by an expression that involves time period. We know the definition of omega. Omega is simply 2 pi by 2. Pi by time period divided by 2. Now we can substitute the quantities given. X is equal to 0.10. Amplitude is also 0.10 meter. Then sine 2 pi divided by Time period is 2.4 seconds multiplied by the time is 0 plus theta. See, we are using this data that correspond to the initial condition at time t equal to 0, x is equal to 0.1. We use this data to calculate theta. And after knowing theta, we can calculate the position, the unknown position x at any given time 0.307. This cancel and we get sine. This is also this is multiplication with 0, so this gives us sine theta equal to 1, and this implies that theta is equal to or pi by 2. Theta is equal to pi by 2. So this is not the only value of theta possible for sine theta equal to 1. Other values of theta also possible. Means all the values of theta that you obtain by adding multiples of 2 pi. You add multiples of 2 pi to pi by 2, you are gonna get the same value for sine theta. But we consider theta equal to 90 degree, that's okay. So theta equal to 90 degree, or we may write it as pi by 2. We substitute this value of theta equal to 90 degree back into this equation. Let us represent. We now substitute theta equal to 90 degree in the equation 1, in this equation, and we get x equal to a sine pi by t plus 90. But sine 90 plus some angle equal to cos of that angle. We can write it as a cos pi by t. So finally we have x equal to a cos 2 pi by t. Now calculate the position at time t equal to 0.3 second. X at 0.3 second. Simply substitute the quantity in the above formula. X equal to a amplitude is 0.10, cos pi by 2.4, time is 0.30 second. This is 0.10 cos pi by 4. Finally, we have x equal to divided by root 2. Cos pi by 4 is 1 by root 2. The unit will be meter. On calculating, we get x equal to 0.0707 meter. On expressing in centimeter, x is equal to 7.07. That is the final answer. Answers to other questions B, C, and D can be found out in the same manner. Question 9. In the problem above, when is the first time the cart is at the position x equal to minus 5.0 centimeter? Solution to question number 9. In question number 9, we have to find time when x is equal to minus 5.0 centimeter, at a distance of minus 5.0 centimeter for the first time. They ask for the first time because oscillatory motion is a repetitive motion. The object will pass through the same position again and again and again. We have to find the first time the object is at a distance of minus 5.0. We can solve this problem again by using the same equation. the equation that we use is this equation. It's x equal to cos pi by t divided by x is equal to cos pi t. So x is minus 5.0. Amplitude is 0.1 cos 2 pi by 2.4 that is 2. Minus 5.0 divided by 0.10 cos 2 pi by 0.4. Therefore, cos pi upon 12 minus we made one mistake here. The position is given in centimeter, 5.0 centimeter, but we have to use in meter as other quantities in all meter for the unit of length. So 5.0 centimeter, 0.5. Correct this. Minus 5.0 centimeter makes 0.0 here, minus 0.5. Therefore, pi t by 1.2 equal cos inverse of minus 0. Cos inverse of minus 0.5 represent the angle at which the cos value is minus 0. And the cos value is minus 0.5 when the angle is cos inverse of minus 0.5 is 120 degree. When theta is equal to 120 degree, cos theta minus, so cos inverse of minus 0.5 120 degree. We cannot simply substitute 120 degree for cos inverse of minus 0.5. We must insert the value of angle in radian unit, because in the description of simple harmonic motion by using an equation x equal to a sin omega t plus theta, in this equation we have already assumed that theta is expressed in radian. So in calculation you must write theta in the unit of radian. In the final answer, you can choose to convert theta from radian to degree, whichever unit you prefer. During the calculation, theta must always be in radian. So 120 degree expressed in radian become 2 pi divided by is this value that we insert. Now it is not only this value of angle for which cos becomes minus 0.5, but any angle which you obtain by adding or subtracting any multiple of 2 pi, add or subtract any multiple of 2 pi, and you get several values for the angle theta. For all those values of theta, cos will be minus 0, because cos function is a periodic function. Also repeat the same value again and again at different values of. So any value can be substituted here, but in the question we have asked when will the object or mass will be at a distance of x equal to minus 0.5 meter for the first time. So we have to find the duration that corresponds to a mass reaching the distance of minus 0.5 meter for the first time. So time value that we have to calculate must be a minimum time value, and minimum time value of course uh, correspond to the angle up to pi by 3 only, without anything added or subtracted through it. So we have to consider only pi by 3 angle value here, pi by 3. Left hand side we already pi t divided by 1, pi get out equal to pi 3 times is second. The answer to this question is t equal to 0.80 seconds. Another way you can make sure that this is the time at which the mass is at a distance of minus 0.5 meter, sorry, 5.0 meter. Yes. Another way you can make sure that the mass is at a distance of 5.0 centimeter for the first time is that the time that you calculate must be smaller than the time period. Time period represents time for one complete oscillation. So when an object passes through a particular point for the first time, the time taken is always based on a time period. And the time we have calculated is 0.80 second, and it is of course less than the time period. It is 2.5 from the answer. This is another interesting question. A block of mass 0.4 kg on a horizontal surface is attached to a horizontal spring of negligible mass. Spring has negligible mass, so we can neglect the effect of mass of the spring on the motion of mass that is attached to the spring. The other end of the spring is attached to a wall, and there is negligible friction block and the horizontal surface. The center of the mass of the block reach a horizontal distance 0.25 meters beyond its equilibrium position. So present an amplitude of the oscillation that the mass will release from this and release from rest, such that the block spring undergo harmonic. A graph of the spring potential energy of the block spring system of horizontal center of mass block is shown. The positive direction is right. On the grid, sketch the graph of force exerted by the spring on the block as a function of block horizontal. We know for sure that the graph between force and position must be a straight line, because force obey Hooke's law. The spring force obey Hooke's law. Force is directly proportional to the displacement from equilibrium position. Directly proportional means the nature of the graph must be. Moreover, we know that when x is equal to 0, the force is equal to 0. Because x equal to 0 represents equilibrium position, the position of no net force. So the origin will always be present on a straight line representing the graph of force versus position. Origin is always 0 force and 0 position. If we could find one more point for the value of force and the position there, then from the 2 points we can draw a straight line and get the graph of force. See, we have been asked to find the graph of force versus position, but we are not given sufficient data. So often when we have to plot a graph, we think about paired values. Paired values must be given so that we can plot them on a graph and get a curve passing through them, a fitting curve passing through. But paired values of force and position are not given. So how do we find the graph? There is a simple. At least one point must be known that is supposed to be present on the graph. That point is x and f equal. We know no other point. We know no other pair of values for the value of x and the value of force there. So we do not get any other point on cannot plot other point at a straight line passing. However, if we could know the slope of the line, then we can draw a line passing through origin having that particular slope, and we will get a graph of force. We can find the slope of the force versus position straight line. We know that the force is directly proportional to the position, and their ratio, which is constant, equal to the spring K is equal to F of by. So if we could find, this is the slope. This is the slope of the straight line passing through origin. Y coordinate upon x coordinate. Y coordinate equals x coordinate x by x is equal to k, and k is the spring constant, and it gives us the slope of graph between force, slope being a straight line. So we will have to find k. If we could find k, we can simply draw the straight line of the k origin. Or you can get another data point giving you value of position and the corresponding value of force. Simply how to find k? We will have to find. We can find k from this graph, the graph of spring potential energy, horizontal distance. Potential energy is equal to half of kx, where k is the same constant that appear here, the spring constant. X is the position. From this, we can calculate k. If you look at the graph, we see that the amplitude of oscillation is already given to be 0.25 meter. 0.25 meter is the maximum distance from equilibrium position, and at the maximum distance we have maximum potential energy. And if you look at a graph, the maximum potential energy corresponds to these 2 points, and the maximum potential energy is 10 joule. And maximum potential energy is at the position of x equal to 0.25 meter. So here we have x equal to 0.25 meter, and the potential energy there from the graph is 10 joule. You substitute for x equal to 0.25 and potential energy 10 joule here. 10 equal to half 0.25 square divided by k. To simplify calculation, you can write 0.25 as 1 by 4, and the square of 1 by 4 will be 1 by 60. K divided by 32. Finally give k equal to 320. The unit of k will be Newton per meter as obtained from its definition upon x. Newton. So k is equal to 320 Newton per meter. We substitute that here, and we get F is equal to minus k. Actually, there is a negative sign. Looks like there is a negative sign. F equal to minus k divided by x. That is, finally we have F equal to minus 20. Now from this equation, you can obtain another data point giving the value of x and the force, and you can plot that data point on the graph and simply draw a straight line. The two. Knowing that, we must know that the nature of graph is a straight line, and then only 2 data points will be sufficient to draw a straight line passing. So another data point can be obtained as follow. We are given that the extreme position is 0.25 meter. We substitute 0.25 meter here, gives us F equal to minus 80. Uh, it is minus 80 Newton. Now you can choose a scale for force choose it as 20, 30, 60, 80, minus 20, minus 40, minus, minus. So second point correspond to x equal to 0.25 and force equal to minus 8. 0.25. 0.25 is here. Second. Now we simply draw a straight line through. That will be the graph. This is the graph between force and next question. Calculate the period of oscillation for the block spring. We directly use formula for the period t equal to pi square root of m by 2 pi of the mass is given to 0.4 kg. We have just calculated the value of k 320. Pi 1 upon can write this as 2 pi upon 2 into 4 gives us pi root divided by 1 upon 20. Pi by 10 root. Pi by 10 root. The answer is equal to 0.2 time period. Next question. A new block of mass 1.0 kg is now attached to the spring. The center of mass of the block is stretched a horizontal distance of 0.25 meter beyond its equilibrium position and released from rest such that the block springs to simple harmonic. The grid below represent kinetic energy of this new block springs as a function of the horizontal position of the center of mass of the block. Change the curve for kinetic energy of the block spring system as a function of the horizontal position of the center of mass. So the first thing that we note is that the graph of kinetic energy is same as the potential energy, except that this graph of potential energy will be inverted for kinetic energy. So having understood that the nature of graph is simply the inverted shape of the potential energy and horizontal position graph, inverted shape. So we want to know what is the maximum kinetic energy. Where will the bottom of the potential energy graph become the top of kinetic energy? Now we want to know where will the top of kinetic energy graph will be and where will the end positions of the kinetic energy graph. We want to know that. We have calculated already the potential energy, the previous example. The potential energy was calculated at a maximum distance of 0.25 meter, which is the same in the present case also. Potential energy at maximum distance is the maximum potential energy and kinetic energy there is 0. So potential energy at a maximum distance is simply the total energy because kinetic energy there is 0. All of kinetic energy is converted. And according to the formula for potential energy, the potential energy at a distance, at a maximum distance, which is an amplitude, we take. And we have calculated maximum potential energy in the previous example. Maximum potential energy in the present case will continue to be the same as that we had obtained in the previous case. The present case differs from the previous case only in the mass of an object, which is 1.0 kg. And from the formula for potential energy, maximum potential energy, which is half kx squared, we see that the maximum potential energy is not affected by the mass of an object because mass appears nowhere in the equation of potential energy. K is a constant that depends upon spring, not upon mass, and A is the amplitude, maximum distance, which is again the same as that in the previous. So maximum potential energy in the present case continues to be the same as the one that we calculated, or that is there in the previous case. Already maximum potential energy is 10 joule. The same potential energy will continue in the present case also, 10 joule. And this maximum potential energy converts to kinetic energy completely when the mass passes through equilibrium position. So maximum kinetic energy is also 10. So top of the graph of kinetic energy will be at this point, corresponding to 10 joule of kinetic energy. This will be the top. Now kinetic energy becomes zero at extreme position, and the extreme positions are at a distance of plus or minus 2 to 0.25 meter. Is represent amplitude because it is the furthest distance the mass was pulled away from the equilibrium position. So when an object is on one side of the equilibrium position, it is 0.25 meter. On the opposite side, it is minus 0.25 meter. So at this point, kinetic energy is zero. So kinetic energy is zero at x equal to 0.25 plus 2 pi and minus 2. So we get the ends of kinetic energy graph. Ends of the kinetic energy graph will be at plus 0.25 and minus 0.2, where kinetic energy is zero. And now we can draw the parabolic graph, which is inverted shape of the potential energy. The graph will look like this. Is the kinetic energy versus horizontal position graph for the present. It might confuse you that another object of higher mass, 1.0 kg, have been used in the present case, and it might in some way affect the kinetic energy. Kinetic energy is not affected. Kinetic energy depends upon mass. It is half mv square. Kinetic energy depends upon mass, so it might give you an impression that if the mass is increased, kinetic energy, maximum kinetic energy may be higher in the present case also. But that is not the case. Maximum kinetic energy not increased when you. This is because kinetic energy does not simply depend upon mass, but it also depends upon velocity. Velocity is reduced for higher masses and making the kinetic energy just the same thing, just the same value. We stop here. Bye.